everyone. So after today's class, you are able to do the homework assignments, homework 2, but not all of them. Let's just take a quick look at it. I think so. All the earlier ones, all the like from 2.1 to 2.7 are pretty old problems from analog, but I just modified some of the problems a little bit. For example, this one just added a little bit more sub problems. And from 2.8, that's a BJT problem, 2.9, 2.10, okay, until 2.10. So after today's class, just get started. Don't wait until the very last minute. Okay, you need a little bit more materials or knowledge, which are going to cover it on Wednesday this week to do 2.11 and 2.12. And that's it. It's homework 2, which is due next Wednesday, I guess. Next Monday? Should be next Wednesday. Sorry for that. So there will be a quiz on Wednesday next week. And there might be a little tiny quiz, a really quick quiz this Friday regarding PN junctions and the depletion region and body effect, CLM, early effect, all this fundamental knowledge for semiconductor physics. Just this Friday. Just be ready for that. That can be a really quick quiz. I will probably just give you 5 or less than 10 minutes to do it. So it should be pretty simple and basic. And today and Wednesday, we'll wrap up BJTs and cover stick diagrams because it's going to be used for the lab next week. So this week's lab is still pretty simple. It's a little bit different than the inverter you did in analog, right? So I have a wider one, similar, but just trying to get more familiar with electric VLSI. Right, that's the plan for this week and next week. Midterm exam is next week, next Friday, right? So I'm going to give you a review, I guess, this Friday or next Monday. Okay. All right, more about BJTs. The first is VBE and IC, right? So what's the current in CMOS transistor, in NMOS? ID is a drain current. Here's a collector current. And IV curve looks like this. What's X, what's Y? What's the X-axis? What's the Y-axis here? IV curve, normally. Y is current, right? So that's VBE. That's IC. So what is VBE? Let's draw the transistor symbol. Here's B, here's C, here's E. That's base, that's collector, that's emitter. And the voltage across these two terminals, or you can say that's a forward voltage across the base and emitter. Why it's called forward voltage? Why is this a forward voltage? If you look at the PN junction, NPN, right? You want to turn on the base by apply a positive voltage across the PN. So this PN junction is forward biased. And this PN junction here, so this is forward biased, right? And this PN junction is reverse biased. To operate this NPN transistor properly, you have to forward bias this PN junction and reverse bias this PN junction. So it is able to operate in the active mode. which will give you the largest current gain. Keep in mind. So if you forward bias this guy, this is actually a diode, right? If you have a diode, you forward bias, what's going to happen? Whenever it's larger than the threshold voltage, there will be a current flow through the pin junction, right? And you even need a little protection resistor because the current will be pretty high. The resistance, internal resistance of the diode can be very low whenever it's being forward biased, when it's conductive. So it's going to blow up this pin junction or the diode. Sometimes you even need a protection resistor. But now this is just a model, right? We just want to tell you, you need to forward bias this pin junction. Remember how that works? So remember that in a BJT, in the NPN transistor, you forward bias this based on emitter pin junction, there will be a little current being injected into the base. Okay, and this current will help this layer, because this layer in the real device, after the fabrication, this is very thin. And you have N and N, they are heavily doped, especially for this one. This is a heavily doped N material, has a lot of free electrons. So this is actually conductive. But however, because there's a P here, it's insulating these two N's. If you only have one piece of N, what's going to happen? This is like a conductor, a piece of wire, or a piece of resistor. Unwell, right? It's unwell resistor. It's conductive, right? Current is going to flow freely. But however, for this guy, you do want to control the current. That's why you need a transistor. You just want to turn it on, turn it off to form a logic, right? So you need an NPN structure because you need a P in the middle as an insulator. But how to turn on this guy? You just fabricate a really thin layer of P in the middle and just inject a little current into this P junction. And after that, so you can turn it on. And after that, you add another voltage potential drop across the C and E. It's called VCE, which is larger than VBE. And all the electrons here, the free electrons here is heavily doped. All the electrons here will be attracted to this positive potential, the anode of the voltage source, because this is super thin. So the electrons will be swept across this thin P layer and arrive here. But you have to turn it on first. Have to turn on this base voltage first. You need a VBE first to make this happen. Okay. But if you turn it on, remember in a diode, we normally do not discuss the details of the voltage change of this diode. We just say, hey, if I turn on this guy, for example, I have a VI. If I turn on this VI, what's going to happen? According to the lecture we had last Friday, I guess. So this is VI. If this is VO, here's a resistor. And this is VO, which is plus minus. What is VO? Whenever you are increasing VI, it's being clipped. 0.7 volts. But there will be a minor change across this diode, probably from 0.5 to 0.7, according to like how much you are turning on this guy. But after 0.7, it will not increase anymore. So the curve looks like the VBE and IC, 0.5, 0.7. It's been turned on, not just exactly at 0.7. After 0.5, there will be a little bit current flow through the diode already. So the curve looks like this. That's why when you are increasing VBE to further, the voltage across this pin junction is not increasing anymore. It's just trying to stabilize it by increasing IC. So we got IC increase like exponentially, but VB is not increasing too much anymore. It's pretty similar to the NMOS transistor. Remember, for the NMOS transistor, that's NPN, right? For NMOS, you have VGS. Here's VGS. Here's ID. That's the IV curve of the NMOS transistor, ID and VGS. Here's the threshold voltage, which is normally 0.8 volts for the 1 micron technology we used just for education purpose, not for the C5. C5 is close to 0. I think it's 0.6 something for C5. Similar, right? Very similar. All right, and there's the equation. There's a function. So I see the function of VBE, and the equation is IC equals to IS times E VBE over VT. Important. So what is IS? IS is called the skew current or saturation current. Saturation current, or it's called a skew current. IS is proportional to these three parameters: the junction area, and the base width, and the temperature. So you can imagine if you are seeing a problem, it's normally a given parameter, constant. It's given. VBE, apparently it is a 4 voltage across the base emitter junction. So what is VT? VT is also a constant. It's a thermal voltage. So it's 25 millivolts at room temp. And we'll never use a different value for VT. It's always 25 millivolts in this class. And now the equations. So we know IS equals to this, okay? And IS is normally in a range of 10 to the minus 12 to 10 to the minus 18 amps. That's a range for IS normally, but it's going to be given, so no problems with it. So given this one, IC, this is from physics, okay? So the IC equals to this, and when the NPN is being operated in the active mode, right? In the active mode, then IB equals to IC over beta, and beta is given, and you normally can find out the value for beta on the data sheet for the NPN. If you buy an NPN transistor, an individual component, and you can find out the beta value on the data sheet. So beta is normally 50 to 200. It's the current gain. And IE, so here's a junction again, just in case we're not familiar with that. CEB, right? So you can imagine there will be IB getting into the junction, and IC. According to KCL, you got two currents. So IE equals to IB plus IC. These two currents are not flowing to anywhere else. It's just merging to the emitter and gets you IE here. So IE equals to IB plus IC. And also there's a relationship between IE and IC. So it's alpha times IE equals to IC. A quick question. So is alpha larger than 1 or smaller than 1? Smaller than 1 because IE is larger than IC. And the typical value for alpha is normally like 0.9 because IB is tiny. So I have a little tiny IB, and IB is being amplified, and you got IC, and merged, you got IE. So IE equals to a tiny IB plus a huge IC, and IC and IE are close to each other because 0.9 times IE will be IC if alpha is 0.9. Important. So what's the relationship between alpha and beta? Let's derive it. So IE, we know that it's 1 over alpha IC equals to 1 over beta IC plus IC, according to this equation. All right, so we can cancel IC. So 1 over alpha equals to 1 over beta plus 1, right? So alpha equals to 1 over beta plus 1, which is beta over 1 plus beta. Let's do the same thing, but we move the 1 to the left. Then 1 over beta equals to 1 over alpha minus 1. So beta equals to 1 over this minus 1, which is alpha over 1 minus alpha. So this is also important. Any questions so far? Straightforward. Right? Just need to remember this first, and you can derive this whenever you want to do it. But in the future, I'm pretty sure you can remember this. But now, if you know these 3 equations, you're good. I think it's the most important one. So IB equals to IC over beta, and beta is normally 100. The typical value is 100. So IB is being amplified by 100 times, so get IC. Okay. An early effect. How to understand the early effect in the NPN transistor? Why it happens? We know that we have to turn on the NPN junction by applying a VBE here. So VBE. Here's a VCE. Here's VBE. In order to operate this NPN transistor in the active mode, remember the active mode? This is cutoff. This is what? Saturation. It's confusing because the saturation in NMOS is here, but in NPN is here. This is active. And you want to operate this NPN junction in this region. So that's this is VCE, this is IC. All these ones are different what? Different VBEs, right? VBE1, VBE2, VBE3, VBE4. All right. And we have to keep, so here's the junctions. how to operate this guy in the active mode. What's the relationship between VB, VC, VE? Here's E, right? Here's C, here's B. Which is the largest voltage? Active mode. Which is the largest? Which node has the largest voltage potential? C. Which is the lowest? E. So it has to be VC larger than VB, larger than VE to operate in the active mode. In that case, this is the largest, the second largest, the smallest. A quick question. Is a BE junction forward biased or reverse biased? The BE junction, forward biased or reverse biased to operate this NPN in the active mode? Forward biased. Is a CE junction, no, is a CB junction forward biased or reverse biased? CB junction. Forward biased or reverse biased? Forward biased means P to P, so the P has a higher potential than N, right? Reverse biased means the N junction has a higher potential than P. So this junction, forward biased or reverse biased? We are not biasing it directly using a voltage source, but however, because these two terminals has a different voltage potential, so it actually has a voltage drop. And you want that voltage drop to be forward or reverse for this pin junction. Reverse biased for this junction. All right, that sounds weird, right? Reverse bias, how can I inject the current in that direction? Because it's super thin, very, very thin. All right, and you have this one is heavily doped. So the electrons can be swept through this very thin layer and arrive this collector. Is that making sense? That's why it's called collector. It's collecting electrons. Emitter is emitting electrons upwards. Okay. So if you have this guy reverse biased, then before you turn on this guy, what's happening? Is there a depletion region? Is there a depletion region? It should have a depletion region, no matter what, right? There will be a depletion because of the concentration gradient, right? There will be a depletion region, no matter what. Can be narrower, can be wider, but there will be a depletion region. And which one has more holes? Which side has more electrons? Which side has more holes? Which side has more electrons? Top one will have more what? More holes. So this has a higher concentration of holes, so the holes will diffuse to the top depletion region. And this guy has more electrons, right? So if I increase VCE, toward the right hand side of the coordinate, of the direction of the coordinate, then what's going to happen for this layer, for the width of this layer of the depletion region? Remember, if we have done this in the diode. We have discussed about this. So if we reverse bias it and increase the voltage, is this getting wider or narrower? Getting wider. Why? How can you remember that? How can you understand this intuitively? If you forward bias it, it's going to be conductive. Why? Because it's getting thinner and thinner, so the electrons can be swept through the depletion region, and so it can make the diode conductive. That's how that works, right? So in the opposite way, if you reverse bias it and you increase that reverse voltage, it's going to be wider because it's trying to against the current flow from P to N. There's only like saturation current flows through it, tiny amount of current. So same here, if you increase VCE, will this depletion region getting wider or narrower? Wider, right? Same concept. It's getting wider. Then what's going to happen? If this is getting wider, the P is already pretty narrow according to the fabrication. And because this is getting wider, so the P is actually being squeezed. This is even narrower. Okay? So which means the electrons will receive more momentum or electric field. So it's getting easier to be swept through this little very thin P layer. What's going to happen is the IC will increase. That's why when VC is increasing, it's not purely flat, it's going to do this. So that's the early effect in NPN. So it's different mechanism behind the scene. It's different from the CLM. What is CLM? Channel length modulation in CMOS. Channel length modulation in CMOS. The same effect here to give you an inconsistent current flow in this region. So what's going to happen is there will be early effect if you draw this, and there will be intersection with the x-axis, and it's called VA. It's early voltage. That making sense? So if you increase VCE, it's getting wider, so the P getting thinner, and it's easier to get more current flow through the junction. So that's why it's getting larger current. Early effect. See, it's ready for examples. So you can imagine in a silicon wafer, that's a structure. Let me draw the structure of the NPN transistor. Structure of actual NPN. You have a substrate a little metal contact, a terminal, a little metal contact, a terminal, a metal contact, a terminal. Is that an NPN transistor? That's a cross-sectional view, right? So if it's a top view, then you can see it's like this, like a donut. NPN, that's a top view. That's a cross-sectional view. So you can, for example, this is collector, this is base, this is emitter. All right. Applications. So the fundamental applications for BJTs are switches, being used as switches. For example, I have a terminal, have a resistor, and a photodiode LED, actually 5 volts here, 5 volts here. Okay. If I turn this on, if I give 5 volts to this terminal, and current flows through this transistor as IC, so to turn on this LED, it's glow, right? So similar to a switch, you can design a push button like that. Push, turn it on, release, turn it off. Easy. Or can use it to, if you replace the LED with a DC motor, so you can turn on turn off the DC motor just by controlling this terminal. And you can definitely use the Arduino digital pin to control it. Give a 5 volts, give a 0 volts, turn on turn off the motor by doing this. You must be wondering, why don't just directly use Arduino's digital pin to control the motor? High current, yes. So sometimes the motor is being driven by like 20 volts, and you just need a little. You need a low power, and fast digital pin to turn on turn off this channel. And 5 volts definitely cannot turn on turn off that motor, so you have to use a switch to indirectly control the motor. If this is 20 volts. Okay. So you can see we have a base resistor here. So the base resistor cannot be too large, cannot be too small, and you have to have it. If you do not have it, so the voltage will directly applied to the pin junction, it's going to blow up the pin junction. Here, you need a resistor to protect it. If the resistor is too high, you are not able to turn on the pin junction. So no current flows through the collector or emitter. If it's too small, it's going to blow up the pin junction. So you have to select the appropriate base resistors for the NPN transistor. Right? Let's see one example here. Five volts, and this is 100 ohms. Resistor makes sense because we really do not need a high resistor, a large resistor here, because this resistor is just trying to protect this LED, but doing nothing else. Normally it's 100 ohms, 200, 300 ohms is fine. 1K gonna make this LED really dim. So I think a few hundred ohms will be appropriate. So this is just working as a switch to turn on turn off this LED. It really doesn't matter if this is being operated with the curve. Does it really matter if it's being operated here or here? It just cannot be operated here because there's no current flow through it. Cannot see the LED glows. It has to be here or here. Ideally here, but if it's here, I think it's fine. You just need a current flow through the LED to turn it on, right? So, but let's check if we can operate this one in the active mode or not. Depends on what's the value here we are being provided to the circuit. So this is 5 volts power supply, and if let's assume we have a 20. Let's start with 1K first. 1K here. Okay. So by looking at the curve, for a problem like this, we really do not care about the tiny variation of VBE. See, as long as it's being turned on, even though there's a huge difference in the current, but the voltage is, just very close to 0.6, 0.7 volts. Let's just use 0.7 volts. So this is 0.7 volts. And what is IB? Can I calculate it? Can I calculate IB based on whatever is given here? Why do we need IB? Because IB equals to IC over beta, and beta is normally 100. Let's just use 100. If you know IC, you know this current, and you know what's the voltage drop across this resistor. And you can find out if this resistor is appropriate or not. Let's take a look at it. So, if you want to know IB, you must know the voltage drop across this resistor according to Ohm's law. And you know this is 0.7 volts, so know it's gonna be 4.3 volts. Right? So IB is 5 minus 0.7 over 1K. What is that? 4.3 milliamps. Right? 4.3 milliamps. So IC equals to beta IB, which is 100 times 4.3 milliamps, which is 430 millivolts. No, 430 milliamps. That's a lot. It's a lot of current. Ampere is a large unit, right? So this is IC is for 30 milliamps. So what's the voltage drop across this guy? This is correct. Maybe, yeah, this is correct. 430 milliamps. Yep. And 430 milliamps times 100 ohms. What's the voltage drop? $43000 millivolts, which is 43 volts. Is that possible? It's not possible. You only have 5 volts here. Right, so it's not being operated in active mode. You assume it's being operated in active mode, but it turns out it's not possible. So it must be the saturation mode. Why is that? Why is it being operated in the saturation mode? Is there any other cases? Are there any other cases or possibilities? So for an NPN junction like this, you need VCE to be larger than VBE. But here, you have a little tiny 1K resistor. It's not super tiny, but it's small. So the consequence is the voltage drop or the current is not being limited properly to a small value. So which means you have a huge IB. And whenever this is being, whenever this is huge, your VBE can be too large compared to VCE. So this junction, this PN junction is not reversely biased anymore. It's being forward biased. So it's being operated in the saturation region. So whenever you have a large IB, you're going to be careful because it's probably going to saturate this NPN junction. So the way to make that judgment is just to simply assume that it is being operated in the active mode. So you can use all the equations to the calculation, and you find out it's not possible. Then you just make a conclusion. It's not in active mode. It's in the saturation mode. And it's not possible it's in the cutoff because you have a pretty large IB here. It's definitely being turned on, but just not in the active mode. We do the similar calculation for the NMOS as well. Right? We just assume whenever you have a huge resistor for the NMOS, you have a huge resistor on the top. Just want to be careful, like 100K. Whenever you see this, possibly this is not being in the saturation mode. It's probably in the linear because the current will be limited. So we will have less or smaller VDS. VDS will decrease. When VDS is too small, it's going to be here, not here. As for NMOS. But for NPN, you do it in a similar way. Just assume this is being operated in active. If it's not, then you just make a conclusion it's not possible, so it's being operated in the saturation mode. Right, just keep in mind. So 43 volts is not possible. So it's being operating in saturation mode, and you cannot use these equations because this current gain only applies to the active mode, not the saturation mode. But there's no equations for the saturation mode, unfortunately. So you have to do it backwards. So you can see if you have a small resistor, here's a consequence. So what if you have a 10K or 20K resistor? What's going to happen? If this is 20K, if RB is 20K, what's going to happen? Job, right? Work hard. All right. What if RB, if we have RB, which is 20K instead of 1K? Do the same thing, right? So what is IB? 5 minus 0.7 over 20K. (0.235 milliamps). So IC equals to 100 times IB, which is 23.5 milliamps. So the voltage drop across this resistor, let's call it RC. So VRC equals to 100 ohms times IC, which is 2350 millivolts, which is 2.35 volts, which is lower than 5 volts. And if you use the 5 volts minus 2.35 volts, you are getting like 2.65 volts. So which is larger than 0.7 volts, way larger than that. So which means you can get your CB junction reverse biased. So you can operate in active mode. That making sense? And so that's the very fundamental operation for NPN junction. And we're going to cover a lot more on Wednesday. But now let's take a look at the digital logic gates you can design by using all these NPN junctions, which is interesting to see because you have been building all these logic gates using NMOS, PMOS, right? But you can also do it using NPNs. So digital logic, it's also called TTL logic, transistor level, transistor logic. Inverter. How to build an inverter? Is this an inverter? That's in. Where's out? So that's an inverter. Because when in is 5, it turns this on, and this will be pulled to the ground. So you're getting 0 volts, and vice versa. That's a pull-up resistor, normally 10K. Okay. So what about AND gate? Can I build an AND gate? How to build an AND gate? A, B, 2 inputs. Where is the output? So I have to turn on, so A and B have to be both high to turn on this channel. So VB will be high. This is a pull down resistor, 10K. It will be pulled up to VDD if both A and B are highs. Otherwise, it's going to be 0. It's being pulled down by this 10K. Right? Because no current, no voltage drop, right? It's 0. What about OR? OR. Where's the output? Because either A or B is on, this will be pulled to the VDD. So you got a high here. You just need a 1 high for either A or B. The output will be high. And if you want the output to be 0, both A and B have to be 0 to turn it off. So it's an open circuit. It's going to be put down to the ground. That's a pull down resistor. Another really interesting application I want to let you know. Let me show it really quick. Here's a connection in here, and that's a motor. Yeah, we'll start from here on Wednesday. We didn't have time today. So that's a H bridge. That's a circuit in your motor driver you have used in microcontrollers and all these robots. I'm going to cover this on Wednesday. All right.